PCN tours the Keystone State, taking you inside Pennsylvania's factories, museums, and historical sites.
Hi, welcome to Pennsylvania Precision Cast Parts. We are an investment foundry that specializes in stainless steel, carbon steels, low alloys, Monels, copper nickels, and Hastelloys. We were formed in June of 1983. Today, we're going to give you a tour of our facility, and we're going to be focusing on this particular casting, among many others. This is a carbon steel gear that is used on trailers that carry cars. We will be looking at it throughout the various stages of our operation to try and inform you and teach you what we do. Our process starts with engineering. So let's walk over and meet Paul Fouts, who's in charge of that department.
My name is Paul Fouts. I'm Director of Technical Services here at Pennsylvania Precision Cast Parts. And I just want to briefly start out and show you how we start a job here at the foundry. The first thing that we will receive from a customer is a print or a CAD file, or sometimes what we refer to as a box of prints or parts. And the customer will have all their specifications and all their dimensions on these prints. We then quote, the first thing we have to do is quote a die, as you can see here, a couple examples, and also we also quote the casting price. We then submit that quote to the customer, and sometimes we get POs within a couple of hours from the quote. Sometimes it takes up to a year. Once we receive a purchase order, we then start the construction of our aluminum dies. The dies take anywhere from 3 to 8 weeks to complete, depending on the complexity. Here's an example of a part right here where we have aluminum die. And then to start the sampling process, we'll shoot a wax, a liquid paste wax, into the die and make a wax. We then put these on trees, or styrofoam trees, which are determined by the engineering department, and run those through the shop. It takes about 2 to 3 weeks to produce a sample off of this tool. We then check the part to the print, do a full, complete dimensional layout, and sometimes there's non-destructive testing that has to be completed. Once that is all completed, the samples are submitted to the customer for their approval. Once the samples are approved, we then turn over the job to our production department and Mike Dissinger.
Our process begins by taking the raw wax which we purchased and melting it in a melter at about 180 degrees. It drops into our conditioning tank where it's processed and held maintained at about 150 degrees. From there, through a hydraulic pump, the wax is pumped to all of our injection stations, which we will now walk into that room and see that. We are now in our wax injection department, where we take that liquid wax that is pumped to each individual machine. The wax is injected under pressure at about 140 degrees. We do have some machines that actually temper the wax down to about 132 degrees. That's called a paste wax. It's the same wax, just starting at a little bit colder temperature, which decreases the dwell time and therefore makes the process go a little bit quicker. Again, the wax is injected into this aluminum die under pressure. It solidifies quite quickly. We can get about one of these every minute, minute and a half. The operator will take this wax, cut off the injection port, which is where the wax went into the tool, and from this, we will take this wax pattern to replicate it and make our casting. If we have an order for 1,000 castings, we need to, first of all, inject 1,000 waxes. We make our part twice, once in wax and once in metal. The tool that Frank is running is a semi-automated tool. It has a series of bimba cylinders which take the poles and push them in and pull them out. Frank is showing you that right now. The wax will go into the tool and go all around the aluminum cavities, therefore giving us the exact shape that we need to duplicate. We make a variety of sizes of parts, anywhere from just an ounce or two up to several hundred pounds. This part is going to end up weighing in metal probably about 60 pounds. The gear that we just looked at weighs about 2 1/4. One of the interesting things about wax is that as it solidifies or freezes, it shrinks. We all think of water as it freezes, it expands. Wax is different. Most liquids shrink as opposed to expand when they freeze. Therefore, to hit the proper dimensions of any tool, the tool must be built with the shrink factors in mind. This wax is actually bigger than the casting will end up being, because once again, when the mold is processed and the molten metal goes into the mold, the metal will also shrink, and therefore there is a 2-stage shrink factor built into every aluminum tool. It obviously takes longer to inject a larger part, and therefore we may only get 30 or 40 of these in a shift, where on the gear we can get about 250 in an 8-hour shift. We are a jobbing shop and have right now about 4,400 different tools that we make. The shot you're seeing now consists of about 25% of our tooling. Some of these tools get run on a monthly basis. Some of them get run on a weekly basis. There are other tools that may only get run once or twice a year. The next step of our operation is to take the waxes that have been injected when a complete order is ready and to assemble them on trees or clusters. What we're showing you now is the process where we build our tree. The styrofoam is used for several reasons. One, it's more economical than using wax spruing, and two, because we're a hand-run shop, it's much lighter for the operators that will be handling the mold as it's being built. The styrofoam that we use is cut specifically for the individual part that will be assembled to it. We glue them together, putting a pouring cup on the top. We're putting holes in the styrofoam, and the holes are so that we can put a handle in. The handle will be used to hold the entire mold on a conveyor system in our dip room. It'll also be what the dip room operator uses to handle it in the dipping process. We're back in our wax department, and we're now in the area where we assemble the waxes to the styrofoam trees. Many jobs are very simple. There's just one gate where the part gets assembled and attached using a stick-tight glue. Other parts are very complicated, and there's a whole series of styrofoam connections to feed different parts of the casting. This particular part has 3 gates: the bottom, the middle, and the top. The metal will get poured down the choker system and enter into the bottom of the sprue, and this part will actually be bottom fed. The metal will rise up to the bottom and eventually fill the entire cavity. Keeping in mind what you see here in a positive will eventually become a negative inside a ceramic mold. This is still just the assembling of our patterns. We have yet to start the molding process. Frank is now attaching the wax patterns that he injected prior to the styrofoam. Getting them on accurately is important for the rest of the operation. He's working on 3 separate trees at a time. He'll now put the second row on each tree. The wax that he's using is called a stick-tight. It'll solidify in about 60 seconds. The trees that are being built here will next enter our dip room. That's the process where we build the shell, the ceramic shell, around the wax and styrofoam pattern. Everything you see in this department will be duplicated in metal. The gears you're seeing now need handles, and then they're ready to go into our dip room. Before the molds can get dipped, they need to be pre-washed. They're put in a special pattern wash for about 15 seconds and gently agitated, which removes the mold release from the injection process as well as any oils or films that were picked up in the handling of the part prior to the dipping operation. They're allowed to dry for a minute or two, then the dipping process can begin. All of our dipping is done by hand. The operator will take the assembled cluster of wax and styrofoam and dip it into a primary slurry. The operator will ensure that he has proper coverage inside all the cracks and crevices to ensure proper detail. He removes it from the slurry, checks for any air bubbles as well as for proper coverage, allows it to drain, and after about 30 or 40 seconds, he'll then take the mold and immerse it into a fluidized bed of zircon sand. The primary slurry, liquid slurry if you will, is a combination of zircon flour, fused silica flour, silica, which acts as the binder, and water. Every part gets 2 coats of primary, 2 coats of the slurry with 2 coats of the stucco. Between each coat, you must have complete drying. This room, as well as the wax room, is controlled all year round at about 72 degrees. The purpose of that isn't necessarily for the operator, it's more for the wax. The wax will expand if it gets too warm. It'll contract if it gets too cold. So keeping an even temperature is critical in this department. Once the shell gets built on that wax, if you have a variety of temperatures, the contraction and expansion of that wax could cause your shell to crack. He's now taking that mold, putting it into a fluidized zircon sand, and the sand sticks or adheres to the wet slurry. He'll take that mold, hang it up, and in about 3 hours, he'll be able to dip that mold again. As you can see, hardly any detail was lost in that initial coat because it's a very, very thin coat. Maintaining slurries is critical to our operation. They have a specific target of viscosity to maintain each individual slurry tankette. They also add additives such as wetting agents and defoamers, which takes care of air bubbles and also helps in the adhering of the slurry to the wax pattern. Once the primary coats are put on, they're moved over to our conveyor system where we have 4 separate backup stations. We're now adding our backup coat. This particular part, the gear that we've been following throughout the entire process, gets 5 backup coats in addition to the 2 primary coats which we just saw. The final coat is what we call a seal coat, in the slurry only. The same thing will happen here as what we saw in primary, just in a different type of slurry. This slurry is made up of aluminosilicate, fused silica, colloidal silica, and water, with a few other minor additives. Again, the same techniques are used. The operator takes the mold, the pattern, dips it in the slurry, makes sure he gets complete and proper coverage, allows it to drain, and then puts it in the fluidized bed. In this case, the sand is an aluminosilicate instead of the zircon stucco that we saw in the primary. So then put the mold back in the conveyor line, get the next one, and repeat the process. On the primary side, it took about 3, possibly 4 hours to dry between coats. On the backup, it takes longer. It could be anywhere from 6 to 12 hours between coats. We have 4 backup stations and 2 primary stations. This department, as well as all the others in our facility, operate 24 hours a day. What you're seeing now is a mold that has been completed. The final coat was the seal coat in the slurry, but no stucco on top. It holds the whole thing together and gives us a nice smooth texture. These molds need to be completely dry before they can go to the next operation, which is the removal of the wax and styrofoam. Remember, inside this ceramic shell is the styrofoam sprue and the wax pattern. Before the metal can be poured into this mold, it needs to be removed. The removal of the wax, first of all, starts with getting rid of the handle. That's a very simple operation. Just twist and pull. What we're doing now is removing the excess ceramic on top of the styrofoam. We need to smooth out the pouring cup as well as to make a complete opening so that the wax and styrofoam can come out of the ceramic mold in the de-wax operation. We just take the very top surface and grind it on a surface grinder, a belt, and smooth it down. We can de-wax 8 molds at a time in our flash fire oven. This oven runs at 1,350 degrees Fahrenheit and will cause the wax and styrofoam to be removed quite quickly. The idea on flash fire de-wax is to cause the wax to become molten and run before it has a chance to actually expand and crack the shell. That's why it's called flash fire. The operator is putting on his gear so he can open up the oven, take the 8 molds that were just completed, and put in 8 new molds. We'll take the molds out one at a time, put them on the floor, allow them to cool. Once they are cool, he'll inspect them for any cracks that may have occurred in the flash fire dewax process. And then the molds are ready to be poured. This particular part, as you can see, has 3 castings per tree. The sprue or styrofoam is in the middle, and the parts are attached to the side. I'll now put the next 8 molds in. The oven has a series of holes on the hearth. The wax will get hot and start to flow and fall into a water bath behind the oven. This oven operates automatically. As soon as the door is shut, the burner automatically comes on and takes the oven temperature up to 1350. We're behind the flash fire dewax oven now, and you can see the wax coming out of the hearth. Again, there's 8 molds inside. It takes about 15 minutes for these molds from start to completion. The wax falls into a water trough, which we have aerated, which just causes a gentle turbulence, which keeps the wax from catching on fire. The wax coming out of the mold right now would be about 180 degrees. Again, we will collect the wax, allow the water to drain out of it, and it can be reclaimed at our wax manufacturer. We have here a completed shell. We had a wax, we had a styrofoam tree, we processed this in the dip room, 2 primary coats, 5 backups, and a seal. We then put this mold in our dewax oven, and what we have now is everything that we had in a positive in our dip room is now a negative inside this ceramic shell. I've taken one, and I've cut it open, and you can see everything that we saw in wax pattern is now opposite. Wherever you see a solid will become a negative in casting form. We'll pour the molten metal inside the mold. It'll solidify, freeze, and hopefully what we had in wax and styrofoam will be replicated in metal. This heat is carbon steel. We'll be pouring gears shortly. Right now the melter is removing the molten slag from the top of the metal bath This metal will be poured at about 3,020 degrees Fahrenheit. Once he's comfortable with the slag removal, he'll do one final check for temperature, and then he'll call the guys that will pour the metal from the furnace into the molds to get the ladle. It takes about 1 hour to melt a heat in. It takes about 15-20 minutes to pour it. Right now he's removing the dirt and debris on the top of the furnace so that when he taps the furnace it won't fall into the ladle, and therefore will keep it out of the mold. The slag comes from all the impurities that are either in the metal or dirt that would be on the metal. Basically, everything melts at about 3,000 degrees, and if it melts, it's going to come to the top. The slag is lighter than the metal, and therefore it does float. They're getting the ladle now. The ladle is preheated with a gas flame. He's going to just try and scrape out some of the liquid slag that was maintained in the ladle from the last heat. The more impurities and slag you can keep out of your castings, obviously the better castings you're going to get. Now that the furnace is ready, the metal is ready, and the ladle is ready, they'll start to get the molds out of the oven. The molds are preheated at 1,800 degrees, and they've been in the curing oven for about 4 hours. This particular ladle that we're using holds about 120 pounds of metal. This mold holds about 35 pounds of metal, so they'll get 3 molds to a ladle. The molds are handed by one operator to the other, and he sets them in the pouring bed. They'll now tap the molten metal into the ladle. They just added a very small amount of aluminum, which acts as a deoxidant for carbon steel. They'll now bring the metal out to the molds. And pour it into the ceramic shell. Remembering that prior to this operation, there was wax and styrofoam in that ceramic. Once those 3 molds are poured, the melter will put a hot top on top of the poured mold. That's put on to induce a shrink. You don't want the top of the part to freeze. You want it to stay molten so that the shrink takes place from the top down. If it would freeze across the top, the shrinking would take place somewhere else and probably get into your casting. It's an exothermic material which keeps the top liquidous. The furnace that they're pouring from right now holds about 700 pounds of metal. We have two melting units, a 450 kW unit and a 250 kW unit. Today we're pouring out of our 700-pound furnace, and on the other side, out of our 300-pound furnace. In addition to those two, we have a second 700-pounder and a 1,000-pound furnace. Again, the molds are at 1,800 degrees, and the metal is about 3,020. In the summertime, this job can be very, very warm. If you scan back to the first three molds, you can see the shrinking starting to take place. Again, we want the shrink to take place from the top of the sprue down, because we know that metal is going to shrink as it solidifies. And the trick is to make it shrink where you want it to, not in the casting. And the hot top helps to facilitate that. Every metal that we pour has a specific chemistry. The melter needs to know what that chemistry is, and he needs to be able to hit it on a consistent basis. We have a spectrometer in the basement which we can run preliminaries on, which tells us exactly what's in every individual heat, and we can make the adjustments prior to pouring. Again, this is a carbon steel. It's basically 99% iron. It does have carbon, manganese, and silicon in there as well. Our stainless steel would typically have 20% chrome, 10% nickel. It could have 2% molybdenum. Other alloys would take tungsten and vanadium and a wide variety of other elements. The ranges many times are within 0.2%, the high and low. So the chemistries can be very, very tight. And every element in each chemistry must be exactly in range, or else we have an off-analysis heat, and therefore you cannot pour the mold. In this ladle, they'll be pouring a test bar along with the three molds. Every heat gets a test bar poured, and from that, we can test the physical properties of the metal. We will test the yield, the tensile, the elongation, and the reduction of area. That test bar will be processed with the castings, heat treated to the same condition that the castings require, and then downstairs in the lab, which we'll see later, it'll get put on the tensile machine, stretched, pulled, and broken, and we'll be able to measure the physical characteristics and the strength properties that the castings have. We're now in our knockout room. This is the process where we remove the ceramic shell from the poured part. It's nothing more than a very large impact hammer, a jackhammer if you will, and it's very loud. Our main goal in this area is just to remove enough ceramic material that we can cut the castings off the sprue. We'll worry about the ceramic inside the part later. Everything you see here used to be wax and styrofoam. It's now metal. Well, we found some more gears. These parts have been knocked out. They're now ready to get cut off. As you can see, this used to be a wax pattern. This used to be styrofoam. We're now going to cut the gears off the sprue. next operation is grinding. We will take the part that we just cut off, and where the part was connected to the screw, there's still a leftover gate. That needs to be removed so that the part is symmetrical. We'll take that, and on a belt with a ceramic grid on, we will take it and remove it. This particular part calls for a flush witness. The surface is exactly even and flush with the rest of the casting. Some parts call for a slight witness, and we may leave 10 or 20 thousandths where that gate was. Larger parts are done on a swing grinder. We clamp the parts in, and then with pressure, run across the surface. The belt is the same. We're just sanding the excess metal from the casting. Our next step is to take the casting that has been now cut off and ground and to remove the excess ceramic shell. We'll put these castings about 100 at a time in a tumble blast. The parts will go in there for about 25 minutes and they'll get tumbled over on a mill belt. They'll be blasted by a 50 grit shot media, very high velocity, and after about 20-25 minutes, they will come out free of ceramic. What you're seeing now is our heat treat oven. Most of our castings get some form of heat treatment. It could be as high as 2100 degrees Fahrenheit or as low as about 950. These particular parts were put in the oven and run at 1700. They're held at temperature for 1 hour per inch. Typically takes about an hour to get the temperature, and then they're held for as long as they need to be. Some parts get air-cooled, some parts get water-quenched, all depending on the alloy and the specific nature of the part. This particular batch gets air-cooled. So just simply take them outside, set them down, and let them cool for about 6 to 8 hours. The next phase of the operation is rough inspection. Each and every part that we make will come to this area and will be looked at one at a time. The operator will inspect each casting for any defects they may see, any positives or negatives. If it's a positive, they'll remove it. If it's a negative, they'll mark it up for a cosmetic weld, go to our welder, he'll add pig wire, repair it, matching the alloy to what the casting is. Then it'll come back, and the rough inspector will then remove and blend the weld down. Here we're rough inspecting our gears. Each part, again, will be looked at one at a time. This particular part we will gauge. We have a specific piece of metal which we will fit test every part to make sure that the part fits on that cylinder, spins freely. If it does, he's happy. If it doesn't, he'll take a little carbide tool and press out any blends that may need to come out in order for that part to fit properly. The gauge that he's using is the exact size of the piece of pipe that will go on when it gets shipped to the customer. We are now in the very final stage of the process. Sam is inspecting the castings and preparing them to ship to the customer. One more look, making sure that they're exactly what we need. If Sam's happy, we're all happy.
This is our final inspection area. All the castings at Pennsylvania Precision are 100% final visual inspected. What the inspectors will do is come over to our QA display, and they'll punch up, go in, find the customer. For example, and here's all the instructions for inspecting the part, any kind of special instructions for packing. You can also go to quality assurance, check to see if there's any specifications there. We'll go to this one particular part. Here it shows you all the inspection criteria, how to check, make sure the gates are ground correctly, what type of defects to look for. There's a gauge we have to use. Sometimes the parts get gauges or fixtures. And we even have sometimes pictures of how to box the parts, so they get a good shipment. So we'll leave the inspection area and go over to another place on the other side here. We do straightening. As part of the final inspection, we have to check the castings, make sure they're flat and straight so they meet the print requirements. The characteristic of steel as it's solidifying, it will always try to bend or deflect in some manner. So one thing we have to do here is check for flatness and make sure the parts are nice and straight. And that's what this fellow over here is doing. He's pressing the parts. A lot of the parts can be straightened by just setting them in these little blocks and pressing on them. Some parts we'll have to build special fixtures to hold the parts just to get the proper bending action. Again, 100% of these parts will be checked because we found that the parts do tend to bend in production. That kind of wraps up our tour here at Pennsylvania Precision here in Lebanon, Pennsylvania. Hope you enjoyed the tour, and if you wish to contact us, we'll list the phone number. And we do have a website. It's ppcpinc.com. Thank you.